Welcome to Speed Up Python with Concurrency. My name is Chris, and I will be your guide. In this course, you will learn what the different types of concurrency are, how to use the 3 standard libraries in Python that cover concurrency, threading, asyncio, and multiprocessing, and when to use concurrency and when possibly to avoid it. Before I get started, a quick note on versions. The code that I demo inside of this course was tested with Python 3.8.5. The asyncio library in particular has been under active development in the last few Python versions. If you want to play around with asyncio, I recommend using at least Python 3.7. Anything before that, and you'll have to make some changes to get the code that you see in this course to work. So what is concurrency? It's the simple act of doing multiple things at the same time inside of your computer. For the moment, just consider a single processor computer. It wasn't that long ago that these were very common in the household. It would be easy to think that a single processor computer was actually doing multiple things at a time, but it wasn't. This was an illusion. Think of it like a film in a film projector. The projector is showing you multiple frames per second, switching between these frames quickly, providing the illusion of motion. A single processor computer is doing the same thing. A lot of computing workloads are I/O bound. This means they're waiting for the disk or network. Because a lot of programs spend a lot of time waiting, your operating system can take advantage of this and switch back and forth between the programs, providing the illusion that multiple programs are running at the same time, when in reality, a CPU can only do one thing at a time. In the last 10 years or so, multiple processor computers have become cheap enough that they've become common at home. This course will talk about the differences between creating concurrency in I/O-bound situations versus processor-bound situations, and the techniques involved in solving both of these kinds of problems. Python provides 3 different mechanisms in the standard library for concurrency: threading, asyncio, and multiprocessing. Threading and asyncio are 2 different mechanisms for handling I/O-bound computing. Multiprocessing is actually how to use multiple processors. Solving I/O-bound computing problems, you use the first 2. Solving multiprocessor problems, you use the third one. One thing to be aware of when dealing with concurrency in Python is the GIL, or the Global Interpreter Lock. For now, just understand that this is a locking mechanism that makes sure only one thing is happening at a time inside of the Python interpreter. When programming for concurrency, the GIL can get in your way, and you have to understand how to use it and how to get around it. To delve into I/O-bound concurrency, you first need to understand latency and processing. So I'll be talking about that next up. In the previous section, I gave an overview of the course. In this section, I'm going to talk about latency and how that leads into I/O-bound concurrency. Consider the basic parts of a computer. This is an oversimplification, but good enough for the level of our discourse. There's a CPU where the math is done. This is the brain of the computer. This is where the actual computation happens. Memory stores what is being worked on, and the CPU works with memory frequently, not only to find out what instruction to run next, but where it stores the data to work on. Memory is generally volatile and is gone once you turn the computer off. So for longer-term storage, there's usually a device like a hard drive. And then finally, there is some set of peripherals. Peripherals are usually used for input and output. This includes things like network cards, video cards, and external devices like keyboards and mice. In order for a program to run, the CPU must first fetch it from storage. The CPU sends an instruction down to the hard drive, asks for some data, and gets it back. That information is pulled into the CPU. The CPU then sends that off to memory. In modern computers, there are ways of skipping the CPU to do this, which speed things up, but for the purposes of this conversation, I'm going to keep things simple. Once the program's been loaded in memory, the CPU needs to get the next instruction from the memory and run that instruction inside of the CPU. That instruction often impacts peripherals, for example, sending something out onto the network. The CPU sends information down to the peripheral card, and then the peripheral card itself sends information to the outside world. Each one of these components runs at different speeds, and this is where latency comes into effect. Consider the lowly nanosecond. That's 1/1,000,000th of a second. To give you a sense of pace, a Intel i7 can run about 100 instructions in 1 nanosecond. This varies from computer to computer, but on the nanosecond scale, you're talking about 10 to 100 instructions is pretty typical for a PC. Now multiply that out by 100. That's about how long it takes to talk to main memory. So every time the CPU needs to talk to the memory, you need to delay by about 100 nanoseconds. Again, modern computers have ways of speeding this up, like L2 caches, but for the purposes of what I'm talking about, let's keep it simple. Taking those 100 nanoseconds and grouping together 10 of them gives you a microsecond, or 1,000 nanoseconds. That's about how long it takes to read 500 kilobytes from memory. A short program. Multiplying that out by 100, and then by 10 again, gives you a millisecond. 1 millisecond is 1,000 microseconds. It takes about 2 milliseconds for a disk to seek, So when you ask the hard drive to look for something, if the read head is not on that position right now, it takes about 2 milliseconds for the read head to be repositioned. 150 milliseconds is about the ping time from the east coast of the United States to Europe. So that's a packet going out across the Atlantic and coming back. There's a huge difference in scale between the instruction level, memory level, disk level, and peripheral level in your computer. There can be a factor of 1,000 or more between different steps in this stack. To try and put this in perspective, let's think about this like a distance. Think about a single CPU instruction as a meter or about a yard. For the purposes of this analogy, they're about the same. To help you visualize, that's about the height of a doorknob off the ground on a regular door. This runs in 0.01 nanoseconds. In 1 nanosecond, you can run 100 CPU instructions of that Intel i7 that I mentioned earlier. That would be 100 meters, or about 100 yards, which is roughly the length of an American football field, or about the length of a soccer pitch, give or take the same thing, plus or minus a few meters. So that memory reference, which takes 100 nanoseconds, that's 10 kilometers, or 6 miles. That's a quarter of a marathon. The best marathoners in the world can run that in about half an hour. 3 microseconds, which is about how long it takes to read 1 megabyte from memory, is 300 kilometers, or 186 miles. That's 3 times the length of the Suez Canal. So now you're looking at large distances on the face of the Earth. Going from memory to disk just makes that worse. Reading 1 megabyte from disk is 82,500 kilometers, or 51,000 miles. That's over twice the Earth's circumference. That read time is only if the disk's head is in the correct position and the megabyte being read is in order on the disk, i.e. it's sequential information. If the head needs to move around, there's a cost to do just that. It takes about 2 milliseconds to do a disk seek. That's 200,000 kilometers, 125,000 miles, or about half the distance between the Earth and the Moon on average. And that ping time to Europe, 150 milliseconds, well, that's 15 million kilometers, or 10 million miles. That's 1/10 the distance to the Sun. The difference between a single instruction and a simple network call is an astronomical amount. These differences are huge and hard to wrap your head around. Let me try it another way to see if I can just hit it home. Pretend that instead of an instruction taking fractions of a nanosecond, it took a full second. Reading that megabyte from RAM would take 2 hours and 47 minutes, or you can run 10,000 instructions in that time. That pesky disk seek, 6 years and 4 months, or 200 million instructions. A seek and reading a megabyte, 8 years, 11 months, just shy of 9 years, 285 million instructions. And that ping time to Europe, 475 years, 8 months, or 15 billion instructions. The gaps between the levels in the computing stack are phenomenally large. And just to make it that much more complicated, that Intel i7 that I said runs 100 instructions, yeah, that's a 8-year-old processor. The modern ones are about 3 or 4 times that. Unfortunately, for the distances in latency, it's easier from a physics standpoint to increase the speed of a CPU than it is to increase the speed of network traffic. As a result, computer processors are getting faster and faster at a higher degree than the network traffic is getting faster. As CPUs get better and better, the latency difference between performing an instruction and going out to the network is getting more extreme, not less. This is why most programs are I/O bound. If you write a program that first accesses RAM, hundreds of instructions could be run in the time that it's waiting. If it needs to access disk, that can be tens of thousands or millions of instructions before the program is ready to run again. And if you have to access the network, it's billions of instructions. This pattern is very common. In all likelihood, your program is I/O bound. It spends more time waiting than it does computing. Next up, I'll talk about the types of concurrency and how to take advantage of this latency. In the previous lesson, I talked about the degrees of latency in the different components of your computer. In this lesson, I'm going to show you how that's taken advantage of to create concurrency. Recall this diagram from the previous lesson. It's common for a program to have to wait long periods of time for it to be able to do the next instruction. It needs to wait on RAM, disk, and network. Time slicing is the idea of the operating system mixing other programs into these wait states. While you're waiting for that network packet to come back from Prague, the computer can insert multiple other programs to take advantage of that time. This time slicing is how a single processor computer can look like it's doing multiple things at the same time. Time slicing for multitasking can be thought of at 3 levels. The lowest level is not having any at all. The olden days of personal computers, the DOS operating system worked this way. You could only run a single program at a time. Cooperative multitasking is when the program willingly gives up the CPU. If you know that you're about to go out to the network and you're not going to need the CPU for a while, you signal the operating system, and the operating system can schedule a different program. In home computing, Windows 3.1 introduced this kind of multitasking. If you happen to be old enough to remember using this operating system, you may recall that at certain times the program would just stop refreshing. That would be because it didn't give up the CPU, but it was stuck in a wait state. So the UI was not being updated because the program had not told the operating system to put it into the wait state. As the name implies, cooperative multitasking requires all of the processes to cooperate with each other. In shared computing, or in the case of a program with a problem, this can be a challenge. So preemptive multitasking was created. The operating system in this case interrupts the program whether or not it's ready. The operating system is responsible for swapping between the different programs. In most operating systems, this is done intelligently. If your program does do a network call, that triggers the operating system to take advantage of it and put the program into a wait state. But it can also do it in the case where the program's being a hog and hasn't given up the CPU. Mainframes have done this from very early on, as has Unix. In the Windows world, NT and Windows 95 is where preemptive multitasking was first introduced. On larger computers, you can have this time slicing as well as multiple processors. On each CPU, you can now have different programs running. In some cases, the same program may also be resident on those different CPUs. In this diagram, programs 1, 4, and 5 are tied to a single CPU, but programs 2 and 3 are across the two CPUs. Part of the operating system's responsibility is scheduling within the CPU and across the CPUs. Not all types of software can take advantage of concurrency equally. The type of concurrency you have can change what kinds of models you would use when creating a concurrent program. Trivial concurrency is that where the different parts of the program can be split apart without concerns for each other. This can usually be achieved when activities within the program are completely independent of each other. This is easiest if there's no shared data between the different components. Consider a web server. You can have multiple clients talking to the web server at a time because each one of those clients don't need to be able to talk to each other. There may be some contention at the disk level, but as you saw in the lesson on latency, a huge amount of processing can be done while a server is waiting for the disk. In the non-trivial case, you have to share data across your concurrent components. When you're thinking about this situation, it's useful to think of 3 steps in processing: input, computing, and output. Concurrency is generally done by splitting up the compute portion, but that may mean that there's coordination necessary for the input and output stages. You may also need coordination amongst the different compute nodes, depending on what kind of algorithm you are running. Using the input, compute, and output model, you can think of programs in 3 parts. A producer is a component that produces data. This might mean reading something off the disk. The worker is the component that does the actual computation. And the consumer is the component that consumes the data or aggregates the output. Consider for a moment doing some image processing on a very large file. The producer portion of your program would read the large image format. The worker portion of your program would do the actual filtering on the image, and the consumer component would consume the result from the worker and write the new image to the hard drive. Depending on the architecture of your program, these concepts might be mixed and matched. Using these 3 ideas, you can introduce different patterns in concurrency. This simple pattern has a producer pushing data to a worker, which pushes data to a consumer. It might not be immediately evident where you can get concurrency here, but because producers and consumers are interacting with the disk, a lot of work can be done in the worker while producers and consumers are working independently. Thinking back to the image processing example, the producer might read thousands of bytes off the disk, hand them off to the worker. The worker could then manipulate those thousands of bytes, creating a result which the consumer would then write to the disk. Unless the worker is particularly computationally intensive, in all likelihood, it will most of the time be waiting for the producer and consumer. But as soon as the worker has been fed data, it can start working. The producer does not have to have read the entire image off of the disk. This can produce some concurrency. A variation on this pattern uses multiple workers. Your producer reads information off of the disk, hands it off to a worker, which begins computation. The producer then reads more information off to the disk and hands it off to a second or third worker. The workers work independently, creating a result, and then the consumer is responsible for writing it back to disk. This pattern is common with the processing of very large images. For the most part, an image can be broken up into components, and image processing can be done on those components independently. This means the workers don't have to talk to each other very often, giving a high degree of parallelism between the work they are performing. A variation on this pattern is for the producer to broadcast. In this case, each worker sees all of the data. It may not operate on all of the data, but as the data is exposed to it, it can continue to work. These patterns can also be mixed and matched. You can have your producers broadcasting to workers, workers talking to other workers, and those workers consolidating information for the consumer. Programming concurrent systems introduces all sorts of new challenges to your software. Some things to consider. You must make sure that you've got execution coordination. Different processes have to be able to sync up with each other. Think of the image processing example. Let's say your image was a megabyte large and split up into 10,000 kilobyte chunks. Each worker could work on one of those 10 kilobyte chunks, but in all likelihood, the borders between those 10 kilobyte chunks might impact the calculation in the chunk of image next door. So although for the most part the workers can work independently, when they reach the borders of the portions they're working on, they may need to speak with other workers. Once you have multiple processes operating, the operating system or the programmer themselves has to determine how memory is allocated across those multiple processes. This is hard enough in a regular program, it just becomes more complicated when dealing with concurrency. Scheduling is about when to determine which processes are active. Thankfully, operating systems have done a lot of work on this. For the most part, when you're writing concurrent programs, you just let the operating system do the scheduling. But of course, that also means you're giving up control, so there may be situations where this isn't ideal. Typically, the reason you're writing a concurrent application in the first place is to be able to get things done faster. And really what you're talking about here is higher throughput, more work done per unit time. How you manage execution coordination, memory allocation, and scheduling can change the throughput on your system, and you might need to fine-tune how these things behave in order to actually see speed up. Somewhat related to scheduling is also distribution. How do you split up the different concurrent pieces amongst the CPUs on your machine or between machines? Writing concurrent software introduces algorithmic challenges. Deadlocks are when two or more components are waiting on each other. If A is expecting B to do something and B is waiting for A to do something, nothing is ever going to happen. And finally, resource starvation may also be a problem. The different components of your program may be fighting for memory, disk space, or access to the CPU. Concurrency can be applied at different levels in Python. The simplest is at the operating system level. This means as a programmer you don't have to really worry about it. You can run Python in a window or in your IDE and let the operating system take care of the fact that other things are happening at the same time. If you have multiple processors available on your computer, you can use the multiprocessor library in Python to have code execute on those different processors. Modern operating systems have a lighter weight way of getting concurrency called threads. Each thread in a program can execute different code. Threads can then be scheduled to take advantage of the IO-bound nature of your program. In addition to having threads in the standard library, Python has another mechanism using coroutines called asyncio. The rest of this course describes the asyncio, thread, and multiprocessor standard libraries in Python and the differences between them. When considering concurrency inside of Python, you have to be aware of the GIL. This is the global interpreter lock. The GIL is a thread lock or mutex that makes sure that only one thread controls the interpreter at a time. This limits the way multiple threads can operate inside of Python. When two concurrent parts of a program operate at the same time, you can get race conditions. If you have this kind of race condition inside of memory allocation, you will get memory leaks. The GIL was introduced to solve this problem. One of the powers of Python is the ability to extend it using C. You can write code in C and plug it in underneath and then have it called by Python. Although this makes Python powerful, it also makes memory allocation challenging. Now you have to deal with memory both at the interpreter level and at the C extension level. The GIL is particularly important when dealing with these kinds of interactions. If you do a quick Google on Python and GIL, you'll find all sorts of opinions out there. It is seen by some as a limitation. Whatever you feel about it, it's deeply nested inside of the interpreter, and removing it is not a simple thing. The original inventor of Python, a gentleman named Guido, has stated that the GIL should only be removed if new code does not decrease the performance of a single-threaded program. This is one of the reasons it's stuck around for such a long time. To be clear, the GIL is an implementation detail of the interpreter. CPython and PyPy both have it, but Jython and IronPython do not use the GIL. So depending on your underlying interpreter, you may or may not run into this. This course was recorded in the fall of 2020. At the time of recording, PEP 554 was being worked on. This PEP introduces multiple interpreters in the standard lib. This concept is something called subinterpreters. CPython already has this idea, and it allows C extensions to kick off multiple Python interpreters at a time. Each subinterpreter has its own GIL, and so C extension level code is able to get concurrency without the challenges of the GIL involved. The interpreters are essentially independent of each other. PEP 554 proposes exposing these interpreters in the Python standard library. This doesn't fix the GIL, but would give programmers access to more tools that allow them to work around the GIL. And as changes happen around the GIL, they could be exposed to the programmers earlier inside of these subinterpreters, hopefully improving the ability to do concurrency in Python. Although the GIL is a challenge, the IO-bound nature of most programs means that you can still do concurrency in Python. In the next lesson, I'll introduce you to the threading library, a good way to do just that. In the previous lesson, I introduced you to the concept of concurrency and different patterns it can take. In this lesson, I'll be talking about threads in Python. As I showed you in the lesson on latency, most programs spend a lot of their time waiting for input and output. Threads allow you to time slice your computation. While one thread is waiting for input, another thread can continue to do processing work. Threads work within the Python interpreter and therefore with the GIL. Significant speedup can be obtained if your software does a lot of disk or network activity. All of the software that I demonstrate in this course is available in the supporting materials dropdown if you want to follow along. In order to demonstrate the difference that threading can make, I need something to compare against, so I'm going to start with a synchronous version of a small program. This program pulls down two different web pages many times. Line 14 is where you'll find the key entry point to the code. This function, called download all sites, takes a list of sites, looks for each of the URLs in the list, and calls the download site function. The download site function, defined on line 8, gets a session from requests, which is the library I'm using to download web pages. On line 10, it fetches the content. In order to provide a little bit of clarity about what it's doing, I'm printing out either a J or an R depending on which website is being read. The definition of the getSession function is a little bit overkill in this case. You probably wouldn't do it this way in reality, but it's necessary for the threading library, so to keep the code consistent, I've done it this way. Let me scroll down so that you can see how this program is called. The list in line 21 is made up of 80 copies of the two different websites that the requests library is going to fetch. Line 26 tells you that it's starting. Line 27 starts a timer. Line 28 is the meat where it actually downloads all of the sites inside of the sites list. Line 29 calculates how long it took for this to run. And then line 30 prints out some statistics. Let's see this program in action. There are 160 URLs being downloaded, 80 from Jython and 80 from RealPython. The J and R indicate when the Jython site or the RealPython site is being downloaded from. This synchronous program is alternating between the two sites. The end result is 160 sites were run in about 14 seconds. I've run this program several different times. The wait time for it varies wildly, and a lot of that depends on how quickly the sites respond and how quickly the network interface on my computer decides to respond. I've seen times for this program as much as triple this execution. And now for a threaded version. First off, you're going to need two more imports. Both are part of the standard library. Line 2 introduces concurrent futures, and line 4, the threading library. Line 7 sets up the local environment for each of the threads. I'll describe more of this later. The download site method on line 15 hasn't changed, it's the same as before. But in order to use the threading library, getSession has to be a little different. Line 9 defines the function getSession. Inside of this function, line 11 gets the session from the requests library, but it only does this if thread local has not been created before. The combination of the use of the thread environment in line 7 and the assignment of the request session to that environment in line 11 allow you to change the number of threads in the program and not break anything. This ensures that there's only one request session per thread. Now let's see the download all sites method. It's changed a little. The concurrent futures library includes a class called threadPoolExecutor. This is what determines how many threads there are. You can instantiate this as a context manager using the with key statement. And then the executor has a map method, mapping a function to some data. Each of the URLs in the sites listing gets mapped to a function, and the thread executor determines when that function is called for which thread. Varying the number of max workers in the execution definition will change how many threads are active at the same time. As a function finishes, the thread will be put back into the pool, and the executor will then assign the next piece of data to the next available thread. Let me scroll down to show you the calling. This is no different. So with some minor modifications to this script, I've changed it from being synchronous to threaded. Now let me show you this in action. Wow, that's significantly faster than before, almost 10 times. To be honest, this is kind of lucky. That's one of the best times I've seen. Let me try it again just to show you. Not as good this time. 7.5 seconds is still impressive though. That's almost doubling the execution from the synchronous program. One thing to notice here is the patterns of the J's and R's. In the synchronous program, it was always J then R, J then R. In this program, it isn't, and that's because the threads are waiting different amounts of time. As Jython or RealPython is more or less responsive, the threads are executing at different rates. At any given time, the executor makes sure that only 5 of them are running, but the order that the download site function finishes in is going to be dependent on the network and the server on the other end. The threaded version of the program was using the n-workers pattern that I introduced in the previous lesson. Download all sites is the producer. It is what manages the list of sites that need to be done. The download site function acts as the worker, and in this case, concurrent futures is dictating that there are 5 workers. And then finally, the executor acts as a collection point. It waits until all of the threads are finished, and once they are, the program continues as before once the pool passes execution on. In this case, the print downloaded gets called. To be picky about it, this program technically doesn't have a consumer. The download site function is throwing out the data and not really doing any computation, so there was nothing to be passed on to the consumer. There's just a collection point where the synchronous program resumes. In the previous lesson, when I described the GIL for you, I mentioned race conditions. These are something that you have to be very careful with inside of threads. The thread library acts inside of the Python interpreter. All of the memory is shared across all of the threads. Consider a case where there are 2 threads using a single requests.session object. Thread 1 starts downloading from Jython, but then gets interrupted. Thread 2 then starts downloading from RealPython, but the session object from the first thread wasn't finished. This is going to cause the request library to fail. One solution to this is to use a low-level mechanism called locking. You manage your resources and lock them so that only one thread can use a resource at a time. This kind of locking is exactly what the GIL is for, but it's at the global level inside of the interpreter. Your code has the same problem. Fortunately, Python comes with a library method that makes this easier. This is the threading local method that you saw on line 7 of the code. It looks like a global variable, but it isn't. The threading library is creating a locked space for your objects that are created once per thread. In the getSession method, a new request session object was created inside of this threading local space. This guaranteed that each thread got its own request session object, and also means that you don't end up with 160 request session objects for your 160 URLs. In the example code I showed you, the max number of workers was set to 5. There were only 5 threads happening at a time. This was done on purpose. Although you're downloading 160 URLs, you probably don't want 160 threads. There's overhead for creating threads. There's also overhead for switching between the threads. If you have too many threads, that means your code spends all of its time managing the threads. So how do you know how many threads to have? Well, unfortunately, it's not an easy answer, and it's going to be dependent on how I/O bound each of your threads are. So you may want to experiment a little bit based on your program. An extremely common pattern in GUI software is for there to be a thread for the GUI itself and another thread for execution in behind. This ensures that the GUI is always responsive to the user, and any expensive computation is done on a separate thread. If you're coming from another programming language, or you've seen the Python threading mechanisms before, you might be wondering about the primitives. The Python threading library also supports the typical thread primitives: start, join, and queue. Start is responsible for creating the threads and calling the appropriate functions. Join is the point in the program that waits for all the threads to finish, and queue is a thread-safe mechanism for communicating between threads. Python has these primitives, but introduced the concurrent futures library in order to minimize the amount of code that you have to write when managing threads. As you saw in the sample program, an executor is responsible for managing threads. It maps data to a function and then maps those functions to the threads managing pools, abstracting away the complexities caused by start, join, and queue. This library was first introduced in Python 3.2, so if you're using something older than that, you'll have to stick with the basic primitives. But if you're using 3.2 and later, you're better off looking at the futures library. So that's threading in Python. Next up, I'm going to show you what can cause race conditions and how they're problematic. In the previous lesson, I introduced you to the threading library in Python. In this lesson, I'm going to take a little side journey and show you what happens when race conditions complicate your concurrent program. I have a little bit of a confession to make. I actually went to school for a lot of this work. My research in grad school was on concurrency and parallelism and distributed computing. And it's been many, many years since I did that. And the one thing I still remember is concurrency is hard. You should always choose carefully whether or not it's the right thing to do. It introduces all sorts of complications. In an earlier lesson, I went through a list, including things like deadlocks and resource starvation, that can be quite complicated. Race conditions are related to deadlock in that the behavior of the program changes depending on the order of execution. This is particularly noticeable when 2 threads share the same memory and objects. The nature of threaded computation means you can't predict what order the code is going to run in, and depending on how those shared objects are used, it can affect the outcome. Locking mechanisms and threading.local in Python can help you, but you have to remember when to use them, when things are local and when they don't need to be local. A surprising number of things that are common tools in the programmer's toolbelt are not thread safe. You've already seen the example of a requests.session. The requests library itself is not thread safe. If you're doing multi-threaded programming with the requests library, you need to make sure that you've got locks in place. Even something as fundamental as print isn't thread safe. It doesn't happen often, but it is possible for two different threads to print at the same time, and you end up with a print buffer partially populated from the first thread, populated by the second thread, and then populated by the first thread, which ends up being a mess on the screen. If you've ever done any server-side web programming, you may notice that logging is the way to go. Python's logger is actually thread safe, and so multiple threads in a web server don't cause this problem. Unfortunately, it does this through locking, which slows things down. And this is the compromise you always have to do with concurrency. The speed up is there, but it's often done at the expense of thread safety. The safest thing to do is assume that the code you are using is not thread safe unless it explicitly says that it is. The program I'm about to show you has a race condition in it. It's also what we in the business call a convoluted example. You'll never see code that actually looks like this, but it does show off the fact that the race condition can happen. Race conditions are Heisenbugs, the kinds of bugs that often disappear when you're looking for them. Things are timed correctly, the bug doesn't happen. Things are timed incorrectly, and the bug does happen. And the timing is all related to how the operating system and how Python schedules the threads and how long each thread is asked to execute. Race conditions can be brutal to try and track down. The heart of this program is this function at line 10. The function named race takes a number of threads, and I'm going to call it starting with one thread and then a few more, and you'll see how it changes based on that. The key part of this function is messy line number 13. This list comprehension generates a list of numbers that alternate between -1 and 1. There'll be 1,000 numbers in it, 500 of which are -1 and 500 of which are 1. The function that will be run in parallel on the threads starts at line 5, and this is the change counter. This uses a global variable called counter, and all it does is 10,000 times add to the global counter the number passed in. What's going to be passed in will either be a -1 or a 1. If this code is run synchronously, the sum total of -1 and 1 should be 0 no matter how many times you do it. Line 15 defines the thread pool, and the mapping happens between the data, which is the list that alternates between -1 and 1, and the change counter that adds that amount to the global. The max workers parameter of the thread pool indicates how many threads to run. If this is called with one thread, the program is synchronous. If this is called with more than one thread, the program will be concurrent. Let's see this in practice. Import the function, and I'm going to start by calling the function with one thread. Since this is synchronous, the race condition doesn't happen yet. And -1 is added to the counter 10,000 times, then 1 is added to the counter 10,000 times, and it does that for 998 more times, the end result being 0. Now let me try this again with a few more threads. That's not 0, and this is the problem. From a mathematics standpoint, the reason this is failing is line 7. You can think of that for loop like a multiplier. In the synchronous case, -1 is multiplied by 10,000 and added. And then 1 is multiplied by 10,000 and added, and you result in 0. In the threaded case, you get partway through that multiplication. So instead of it being 10,000 times -1, it might be 500 times -1. And then the other case comes in. That might be 600 times 1, giving you a delta. The sum total of the multiplication factors is not the same as the synchronous addition, so you get a race condition. You get the wrong number. Not only is it the wrong number, it's not even consistently the wrong number. If I run this again, I get a different result. And this is because the scheduling changes how things are happening. The effective multiplier in line 7 is different this time through because the amount of time each thread is run is different, and you get a different number. Third time's the charm? Well, still not working. This is an exaggerated example. I've done it on purpose to show you what happens. Race conditions generally are far more subtle than this, and it would be far harder to find the problem if 1 in 100 executions actually caused the bug to happen, and that's a common result in race conditions. It makes them nasty to find. I'd like to tell you that asyncio solves the race condition problem. Unfortunately, it doesn't, but it is another way of programming concurrency in Python and is of interest. In the previous lesson, I showed you the danger of race conditions. In this lesson, I'll be discussing the asyncio Python library. Asyncio was introduced in Python 3.4, and there are changes in the library as recent as 3.7. The threading library, shown 2 lessons ago, is dependent on threads supported by the operating system. Asyncio is Python-specific. It is independent of the operating system threading mechanism. This gives you finer-grained control over your concurrency. The concurrency model uses something called event loops and coroutines. There is a main loop that happens inside of Python, which controls the order of things happening, and your coroutine is the code that is being run. Inside of the code, you signal that you no longer need control, and you give up execution. The event loop then schedules the next coroutine. This is cooperative concurrency. If one of your tasks doesn't give up its turn, the other tasks starve. But seeing all of this is happening inside of your Python code, you aren't fighting with some other program having to be cooperative. It's your own code you are in control over. So as long as you write good coroutines, you won't have a problem. Asyncio is built on 2 keywords, async and await. Async indicates that code is to be run asynchronously, and the await keyword is the cooperative signal that your coroutine is willing to give up execution control. The biggest challenge with asyncio is that it's still fairly new. To take advantage of it, the libraries you are using have to support it. As an example, the requests library doesn't currently support asyncio. The threaded web fetcher that I showed you in an earlier lesson needs to be rewritten using a different library to achieve the same thing in asyncio. AIO HTTP is a library similar to requests, but it is asyncio aware. I'll be using this library in the following examples. You'll need to do a pip install to make it available to yourself. It's not part of the Python standard library. This is the asyncio version of the web downloading program that I showed you earlier in both synchronous and threaded varieties. The concept's the same. The web page at Jython and our web page at RealPython are being downloaded 80 times each. Line 6 is the definition of download site. This is the part of the code that will be run concurrently. The function takes 2 parameters, a session, which is an object from the AIO HTTP library, and the URL to download. Notice the async keyword at the beginning of the function, indicating that it is going to operate asynchronously. Line 7 is a context manager using the session object's get method. This is what actually fetches the web page. The context manager is also marked as async. Inside of the body, the response object is populated, and like before, I'm printing out a J or an R depending on the URL and printing something to the screen so you can see the downloads happening. Line 11 is the download all sites method, similar to the one in the previous code. Like the download site mechanism, this is also marked as async to indicate that asynchronous code is happening within it. Line 12 is what creates the session object that is going to be passed into the download site function. The asyncio library divides things that are being executed into a concept of tasks. You can examine the tasks as they are running, and so they are collected and returned. Line 13 creates a list where these tasks are going to be stored. Line 15 is a future. This is similar to the concept of the pool. The download site method gets called inside of the asynchronous mechanism, and a task is returned. The download site method is the coroutine. This is where the execution happens. The ensure future method makes the event loop aware that this code needs to be run. It returns immediately with a task, and eventually the event loop will run it. The task itself can then be stored in the list, so at a future time you can check what is running, what isn't running, and if anything fails. Line 18 is the gather method. This is similar to the join method in the threading example. This tells asyncio to wait here until all of these tasks are complete. The list of tasks is passed in, and return exceptions changes the behavior of this method if something goes wrong while the task is being executed. I'll come back to this later. Now let me just scroll down so you can see the main code. The list at line 21 is the same as before. Like before, I'm printing out a message and starting a timer. Lines 28 and 29 are the key parts of executing the event loop and calling the asynchronous methods. Line 28 gets a handle to the event loop, and line 29 schedules the asynchronous download all sites method and says that it should run this method until it completes. So line 29 is where the futures get registered, and then where the gather method is called, and once all of the futures have been performed, the gathering finishes, and this line would return. Line 30 and 31 are similar to before, that it finishes the timer and then prints out the result. Here it is in practice. Once again, concurrency is significantly speeding up the program. Notice the pattern of J's and R's. Like the threading library, you have an inconsistent back and forth between the downloads. You don't have JR like synchronous. The event loop determines when the futures happen and how much time gets allocated for each of the sections of coroutines. Let's drill down a little more on the call to gather. Notice the return exceptions parameter. In the code, I set this to true. The value of this parameter indicates what to do if something goes wrong inside of the coroutine. Your choices are return exceptions equals false, which means the exception will filter up and stop your program, similar to asynchronous execution. This is the default behavior. Or you can register the exception inside of the task object. Returning exceptions true means to return the exception into the task object. There's pros and cons between these different mechanisms. The default allows you to catch problems inside of your code because the exceptions happen like you would expect them to. But what if the exception is being caused by just one execution of one of the coroutines? Do you want everything else to die? And that's why this is a choice. By selecting return exceptions equals true, all of the tasks can operate, and then you can introspect them afterwards to see whether or not some succeeded or failed. If you're creating a new asynchronous program, I would recommend leaving the default behavior on until you've debugged the code. Then switch exceptions true while you're running your actual code so that you aren't interrupted if something goes wrong inside of only one of your coroutines. At any time during execution, you can call the result method on the task object. If the task executed successfully, then you will get back whatever the coroutine returned. If the task caused an exception, then that exception will be fired when you call the result method. You can also request that the event loop cancel running tasks. If you've done that, then this task result method will return the canceled error exception. If you call the method too early and the task hasn't finished operating and hasn't been canceled, you'll get an invalid state error. There are other methods on the task object that allow you to see whether or not it's been canceled, whether or not it's finished, and to introspect as you go along in your code. The Python threading library and the asyncio library solve similar problems. They're both for concurrency in IO-bound functions. So why would you choose one over the other? Because async.io's concurrency is managed by Python, and it doesn't have as much overhead as the threads in an operating system, it generally tends to outperform threads. That being said, as you've seen from the code, it's a little more complicated to actually implement. And as I mentioned earlier, async.io is still new. Your favorite library might not support it yet. Changes are coming, and it's being implemented slowly across a lot of libraries, but your mileage may vary. If a lot of the coders that you're working with are used to other languages besides Python, the threading library's approach is probably more similar to what they are accustomed. Finally, threading is preemptive. Async.io is cooperative. If you're in complete control of the code, this probably doesn't matter all that much, but it's an implementation detail that you may want to pay attention to because it could affect the design of your code. Up until now, I've been showing you concurrency in IO-bound situations that run on a single processor. In the next lesson, I'll show you how to use multiple processes. In the previous lesson, I introduced you to event loops and coroutines using the async.io library. In this lesson, I'm going to show you the multiprocessing library. Both the threading library and the async.io library operate inside of a single Python interpreter and therefore are encumbered by the GIL. If you're doing IO-bound concurrency, this typically isn't a problem. You can still get speed up because of the long latency waiting for network or disk access. Python has a library called multiprocessing that allows you to spin up an interpreter per CPU. This allows you to do CPU-bound concurrency. As each CPU gets its own instance of the interpreter, the GIL isn't a problem. You get one GIL per CPU. This is the multiprocessor variant on our download program. It looks remarkably similar to the threading example. Line 2 imports the multiprocessing library. Line 8 sets a global session. Because each processor will get its own interpreter, each interpreter has its own memory footprint. So when the CPU-specific function gets launched, it will need a session. The creation of this global session is happening inside of this function. The download site method is very similar to before, simply using the session to do a get on the URL and getting the web response. Line 15 is slightly different. This time, instead of printing out a J or an R, I'm going to print out the number of the CPU that the code is running on so that you can see how things are swapped between them. The download all sites method, starting on line 18, has a pool in it. This time, instead of being a thread pool, it's a multiprocessing pool. Unless you specify otherwise, you will get one interpreter per CPU inside of your computer. The initializer parameter specifies a function to call once each of the instances is set up. In this case, this is where I'm setting up the request session. And just like the thread library, a map happens between the function that does the processing and the data in question. The pool.map function takes care of assigning the site values to one of these functions, spreading out the computation. Let me just scroll down. This should all look fairly familiar. Line 32 calls download sites and completely abstracts away any of the multiprocessing going on. Time to see it in action. And there you go, just under 2 seconds. Once again, a significant speed up from even the best synchronous time. Notice the lack of pattern in the CPU numbers being printed out to the screen. Keep in mind, this doesn't have to do with the scheduling of the processes, but when the web server comes back. Printing of the CPU number happens when the web page has finished downloading. So depending on connection speed and network latency, things move back and forth between the CPUs. Because there are 4 interpreters in this case, 4 things are happening simultaneously. Now there's still only one network card, and that network card can only do one thing at a time, so there is a bottleneck, the peripheral, but the CPU components of it operate independently. The key lines of code to using the multiprocessing library are the creation of the pool and the mapping of the data. By default, the pool creates one process per CPU in your computer. Each process has its own memory space, and the initializer parameter is called once per process within the local memory of that space. In the case of this example, there are still 160 things to download. So as a single download site function finishes, the pool assigns the next one to whatever CPU is currently idle. This could account for some of the numbers repeating themselves. If CPU 4 happens to be freed up, while 3, 2, and 1 are still waiting on the I/O, 4 would get the next download site, and if for whatever reason it happened to be able to download quickly, it might print out a result before one of the other 3 processes finished downloading their site. And once again, because each CPU gets its own instance of the interpreter, you no longer have the problem of the GIL. So if multiprocessing partially solves the GIL problem, why wouldn't you just do this all the time? Well, first off, it requires a lot of overhead to create a process. The implementation of a process happens at the operating system level, so you will also see behavior and scheduling differences between operating systems in your code. Because each process gets its own copy of the interpreter, it tends to require more memory than threading does as well. And not only does it require more memory, but you have to spin up the interpreter, so the initialization time of each process tends to be longer than threads. In fact, threads were introduced into operating systems as a lightweight way of getting around the overhead involved in processes. Because each process has its own interpreter and does not share memory footprints, communicating between the processes must be done with explicit constructs. The multiprocessing library comes with a few that can help you do that. Queues and pipes are ways of sending data from one process to another, and the value and array constructs allow you to share memory between processes. The multiprocessing library includes locking mechanisms to make sure that you don't end up with race conditions or deadlocks when 2 or more processes are trying to access the same chunk of shared memory. The number of threads that you instantiate generally can be as many as you want. More is not always better, but it's under your control. Multiprocessing typically is only used to map processes to CPUs. You can instantiate more interpreters than CPUs, but it doesn't really make sense because then all you're doing is swapping out those, and the overhead of the swap tends to be more expensive and you don't actually gain any speed up. Threading and async I/O tend to be beneficial in I/O-bound situations. They are not beneficial in CPU-bound situations. That's where multiprocessing reigns. So in the next lesson, I'll show you the differences. In the previous lesson, I introduced you to the multiprocessing library in Python. In this lesson, I'm going to show you the difference between I/O-bound and CPU-bound workloads. So far, you've seen how to use the threading, async I/O, and multiprocessor libraries. All of the examples up until now have been I/O-bound. In an I/O-bound program, the vast majority of the time the program spends running is in waiting for input and output. Downloading content from the web is a perfect example. The amount of latency involved in network transactions far outweighs the computation involved in downloading it. Not all software is I/O bound. If you're doing heavy mathematical computations, then most of the time is spent in computation. The threading and async I/O libraries only see speed up in I/O bound cases, and that's because they are scheduling computation while the other threads are waiting for the I/O. You get speed up because you're not waiting for one piece of I/O at a time, you're waiting for multiple pieces of I/O at a time. In the examples so far, you see about a 7 times improvement against the best case scenario of a synchronous program when downloading 160 items from the internet. You may have noticed that this speed up is about the same across threading, async I/O, and even the multiprocessor library. If your program instead is doing something that requires a lot of work inside of the CPU rather than waiting on a peripheral, then threading and async I/O is not going to give you that kind of improvement. To get improvement in CPU-bound software, you need multiple CPUs working simultaneously. The multiprocessor library does allow you to do this. In the next examples, I'll show you the differences. This is the synchronous version of a CPU-bound program. It's a bit of a convoluted example. It calculates the sum of the squares between 0 and a large number, and in this case, it does that 20 times for the numbers 5 million through 5,020,020. Line 4 defines the function where the calculation of the sum of the squares happens. Line 7 is the wrapper function that uses a loop to call the calculation once for each of the numbers being passed in. And then inside of the main section, line 12 defines a list, the numbers 5 million through 5,020,020, to run this calculation on. Let's see this in practice. I sped that up so you didn't have to sit there and watch that, but it took just under 9.5 seconds. You may recall from the synchronous version of the download program that there was a large variety in how long it took the program to run. And that was because you're dependent on the network, the response of the server, how many other people are hitting the server at the same time, and all sorts of things outside of your computer. By contrast, CPU-bound programs tend to be consistent. Let me run this again so you can see it. Again, I sped that up, but it took about 9.4 seconds, so roughly the same amount of time. Because this program is spending all of its time exercising the CPU, the only thing that might slow it down is if the operating system is swapping it out for something else. It's not having to wait on any I/O. And now, here's a threaded version of the software. The calculate method does the same thing, the sum of squares. Find sums has changed slightly. In this case, instead of just looping through all of the numbers, it creates a thread, one for each of the 20 numbers to be executed on. It then maps that number to the calculate method, so the numbers 5 million through 5,020,020 will each get their own thread for the calculation. Let's see what happens. Well, that's not good. Because this program really isn't I/O bound, once it's loaded into memory, all it's going to do is do calculations on the CPU. All of the speed up before was by taking advantage of the latencies of going to the peripherals. That's not happening in this case. The reason this is taking longer is because there's overhead in creating and managing the threads. In this case, you're spending about half a second to manage the threads and getting no advantage whatsoever. To speed up something that's CPU bound, you actually need more CPUs. Threads, or async I/O, which are essentially the same kind of concept, will not give you any speed up, and in fact can cost you time. This is the multiprocessing version. The code is essentially the same as the threading version, but lines 9 and 10 replace the threading pool with the multiprocessing pool. Here I go. That's significantly better. It's a little better than a 3 times improvement over the synchronous version. Because this is CPU bound, throwing more CPUs at it does speed things up. The computer that I'm running this on has 4 CPUs. Notice that it's not 4 times better, it's only 3 times better. Creating and managing the processes takes time. There's overhead involved in this. For this calculation, it's about a 25% cost. Donald Knuth said, "Premature optimization is the root of all evil, or at least most of it, in programming." What he means by this is, write your software first, figure out where the bottlenecks are, and then improve on those bottlenecks. Most programmers do not actually have an intuitive grasp on where the bottlenecks in their software are. Every time I think I've known where it is, I've been wrong. You're much better off writing your program first, measuring your program, and then figuring out how to improve it. This leads to the question, when do you use concurrency? As you've seen, moving from synchronous to concurrent software has additional complications. There's more code. You have to decide which type of concurrency you're going to use. You have to worry about thread safety and memory sharing. And then, of course, if you didn't write the program right, you might end up with deadlocks or resource starvation. So the first thing you really want to do is ask yourself, do you really need it? There are certain domains where it makes an awful lot of sense. If you're building a GUI, you probably want the GUI to be responsive, so having it on a different thread than the computation makes sense as a design. If you're doing a lot of data computation, then you want to take advantage of the fancy computer you bought and use all of its cores. I'm not saying don't do concurrency, just make sure that you aren't incurring the overhead of creating the more complicated code unless you actually need it. Once you've concluded that you do need it, you need to decide on a model and therefore a library to use. The easier question is I/O bound versus CPU bound, leading you to decide between multiprocessor or thread and async I/O. If you are doing I/O bound, then you should favor async I/O over threads if you can. It tends to be a little lighter weight and a little faster. That being said, the libraries that you're interacting with may not be compatible with async I/O, so you may be left with threads. Next up, I'll give you a course summary and point you at some further reading if you want to dig in deeper. In the previous lesson, I talked about the difference between I/O-bound and CPU-bound workloads. In this final topic, I'll summarize the contents of the course and point you at some further reading. Different programs use your computer in different ways. A lot of software is I/O bound, spending most of its time waiting for the disk or network in comparison to the amount of cycles available to do computation. Some kinds of problems are CPU bound, meaning they spend most of their time using the CPU to do work. A large amount of latency is involved in getting off the CPU and going to memory, even more to disk, and even more to going to the network. Single processor computers are able to look like they're doing multiple things at a time because they're quickly switching back and forth between programs, taking advantage of this latency. This simultaneous work is called concurrency. This course introduced you to a number of patterns to help you think about how the concurrency works. The first was pipes, starting with a producer responsible for feeding data into the computation, having a worker to work on that data and do the computation, and then having a consumer that consolidates the output of the worker. The n-workers pattern uses a similar model but multiplies the number of workers. This pattern is particularly useful in CPU-bound computing. Having one worker for each CPU can drastically speed up your program. In the n-workers pattern, the producer breaks up the data and passes chunks on to each of the workers. The broadcast pattern is a variation on this where the producer sends all of the data to each of the workers and the workers themselves decide what to work on. Python includes 3 different modules to meet your concurrency needs in the standard library. The first is threading, which helps you do I/O-bound processing and is tied to the threads inside of your operating system. The second is async I/O, which is an event loop and coroutine mechanism that is similar to threading, but is completely contained inside of the Python interpreter and isn't operating system dependent. And last is the multiprocessing library that allows you to spin up multiple interpreters across the CPUs on your computer. When thinking about concurrency in your software, the first thing you need to do is decide whether or not you really need it. There's additional overhead and more code necessary just to manage the concurrency. So make sure that you're actually going to benefit before you write that code. If you are going to use concurrency, determine whether or not your problem is an I/O bound problem. If it is, then threading or async I/O would be your answer. If it isn't, then you need to use the multiprocessing library. In the case of an I/O bound program, you should prefer async I/O over threading if you can. It tends to be more efficient and requires less overhead. Not all libraries support async I/O, so this decision may actually be made for you, depending on your third-party library needs. Finally, be careful with your concurrent program as to how you're dealing with memory and the interactions between the parallel portions of your software. Threading and async I/O use the same interpreter, so you have to be careful about race conditions messing up your results. In the multiprocessing situation, you don't have this problem, but you need to do extra work to get the different processes talking to each other and sharing values. If you'd like to learn more about latency inside of software, these 2 articles are helpful. The second article is the original, and the first article was written by somebody else doing an update on the numbers. This is where I got a lot of the data about component timing inside of the computer. The general purpose concurrency article in Wikipedia gives you a high-level introduction to the topic and points you to different models and ways of thinking about it from a computer science perspective. If you want to learn more about the GIL, there's an article available on RealPython, or you can go to the Python wiki to see some internals. If you're interested in the sub-interpreters, PEP 554 has the proposed changes, and this article on Medium discusses the pros and cons of the approach. If you're interested in threading without using the futures library, the Python docs is probably the best place to start. Or you can read this introduction on RealPython. Generally, I wouldn't recommend using the old school methods. Take advantage of concurrent futures if you can. More information on these can also be found in the documentation. If you want to dig into async I/O, here's a good article introducing you to the concepts. And this conversation on Stack Overflow goes into great detail about how it actually works. This is the link to the multiprocessing library, and this is an excellent article that introduces you to the different concepts. Finally, if you want to up your concurrency game, there's nothing like making things concurrent across multiple computers. This is referred to as distributed computing. This used to be something that was extremely difficult to do unless you had a rack full of servers available to yourself. Now, with the advent of Amazon Web Services, Google Cloud Platform, Azure, and other services like it, you have access to someone else's large warehouse filled with computers. This page of the Python wiki shows different tools that you can use for doing distributed programming. And then finally, Dask and Celery are 2 common Python libraries that you can use to attack these kinds of problems. Thanks for your attention. I hope this course has been useful for you.